Rupak, take it away.
Do you see my screen?
Yes, we see your screen.
Okay. And do you want to record it?
It is being recorded now. So yeah, go ahead.
Okay, so this is the initial Gkeyll simulations for ASDEX with the parameters of ASDEX SOL script of layer, and we are trying to capture the profiles of the electron and ion density and temperatures that has been measured experimentally. This work is done using the Gkeyll's simulation algorithms, and this is in collaboration with Noah Mandel, Mana, Francisquez, Amar, and Ray. So first thing is that what we are simulating the SOL region, the scrape-off layer of the ASDEX or any tokamak, and we are in the bad curvature region, which is around the outboard midplane. So basically, this region, this is the view at a fixed toroidal angle. So we are simulating this region. However, we do not have shear, at least for these runs, for these results that I'm showing now. So we basically straighten the field lines. So it's like this. Actually, it is a helical field line going like this. And we are simulating it in 5V, that is 3x and 2V, gyrokinetic simulations with magnetic field line following coordinates. So our coordinate system itself, the z direction is helical and follows the magnetic field lines without any shear. What are included? We are simulating the full distribution function so that we can have more nonlinearities. We can capture the turbulence better. We have in electromagnetic simulations, so we do not run into any issues with ampere cancellations. For further details, you can see Noah's paper in 2020. We are simulating this with discontinuous galloping algorithm on helical magnetic field line following geometry, and we have Leonard-Bernstein collision operator. We have cross-species collisions, and we are using realistic deuterium mass ratio. The boundary conditions are perfectly conducting in radial direction, and periodic in the binormal is the y direction, which we will be showing in the movies the y direction, and we have a conducting sheet model boundary along the magnetic field line or the z-axis. At least in these simulations, we do not have X points, neither do we have effects from neutrals, no shear, and the collision operators are independent of space and time. For further details about the algorithm and the geometry of these things, you can see presentations by Noah in the Gkeyll website. So for these simulations, we are using, mostly we are using parameters from this paper, from Daniel Carallo's paper, Nuclear Fusion. The electron density for two different runs are these. These are the experimental inputs, and these are the inputs for specific runs. And our numerical inputs for Gkeyll are exactly, we are taking the same density which are around the separatrix, at the separatrix from these papers, but we are using it as an initial condition of our simulation. So we just start with these densities. These are the electron and ion temperature. These are also the initial conditions. And we let the profiles evolve with time, and this electron and ion densities self-consistently evolve, and then at a steady state, we are trying to measure, to compare our numerical results with that of the experimental results. Few plasma parameters are these for understanding. And if we go to the next slide, here you can see. So this is basically the geometry, this is the z direction, which is the toroidal direction, and we have straightened it in this. So this is the helical toroid or helical direction, And this is the position of the SOL, or the scrape-off layer. And this red line is basically the separatrix. And you can see these are some isosurfaces of density has been plotted, ion density has been plotted. You can see there are some blobs coming out because of this, mostly because of this E cross B drift. This is the view at the same frequency, at the same color scale, at the plane z equal to 0. So here you can see that the blobs that shear off from this region and they propagate radially outwards. This is how they increase or enhances the turbulence in the SOL region. And finally, when they go down through the Z direction, it spreads the heat load throughout the divertor. And this is how we achieve the ion heat flux to the lower divertor, which is spreading all throughout a very big distance throughout this major radius. This is fully electromagnetic. So this is 50 times enhanced the fluctuation of the magnetic fields. So these magnetic fields are basically, this is the fluctuations that has been captured, and this is done for the realistic radius and the power of the ASDEX experiments. So this specific simulation has been done for parameters similar to ASDEX short 33292. Regarding the measurements, we have of the order of the similar profiles, the numbers for the electron density in the far SOL region, also the ion density. We can compare this. This is in the log scale, so this is in the normal other scale. However, the numbers, even though they differ at these separatrix, but they match closely in the far SOL region. Similarly, the same thing has been observed for the, we are close to the electron and ion temperature that has been observed for diffuse shocks. One for this
sorry to interrupt, but everything is so small that I can't really recognize anything. Would you mind taking us through what the different curves are?
Oh, sorry. So these are the electron. These are the curves for the high density of the electron and ion. These are also is the low density for electron and ion. The same color scheme has been taken here also. So these are the this curve is for the high density of electron. This one is the low density of electron, and this is the high density of the ions, and this is the low density of the ions. This is the temperature. Sorry. And we measure the statistics of turbulence. So radial particle flux for two different density cases. And these are the fluctuation of the density, skewness, kurtosis for two different cases that I mentioned in the previous slide. And in the next case, we measure the individual blobs. How do they propagate radially outward? So basically, we have a gradient of magnetic field in this radial inward direction. And so we have velocity of something like a polarization electric field because of this gradient of magnetic field, and that causes a E cross B drift in this direction. And because of that, the blobs come out through the radially outward direction, and they fill the whole scrape-off layer region. Regarding scaling, it has been found that if they are connected up to the sheet, the blobs, the velocity of the blobs goes as delta to the, this is the y width of the blobs. This goes as delta to the power -2, and for the other case, it goes as delta to the power ½ And this detached scaling can occur because of these collisions, etc. We measure these statistical quantities from ASDEX experiments and our Gkeyll data. So for these two runs, we seem to be close to the experimental parameters. And we seem to be having, for the high density case, we seem to be having some, even though it's not exactly at the same value of lambda, the collisionality, we seem to be having more bigger blobs, this kind of transition that has been shown, not exactly at the same value, but we are in the ballpark of capturing these blobs statistics. Similarly, for the velocity also.
Sorry, maybe on that last slide, can you say again, what is the?
Oh, the bigger blobs are basically the average values, and these smaller size things are basically the scattering on the other values that we have observed. This value, this is like average of all the blobs that we have observed.
Okay. So this is a plot of the blob size versus what parameter?
Collision. So the same thing goes.
Okay.
And this is again regarding the blob size with respect to velocity. So again, these are the like 1 or 2 blobs of these sizes, and these are like the averages of all size blobs, etc. for these two different runs. We don't really see a very big blobs like this that has been observed in the experiments. However, there are very few points here or maybe we need to go for further higher density scans. And finally, we measure the heat load at the diverter. That is also of the order of 10 to the power 7, which is close for the high density case. This is close to 7 into 10 to the power 6, which is like close. For the comparison of the ion heat flux at the lower diverter. In summary, we have a full-F electromagnetic gyrokinetic simulation using Gkeyll computational framework, and using this framework we can capture the essential features of the SOL turbulence for experimental parameters close to ASDEX-U. And even though the temperature of the ion and electron source are the same, the final ion temperature is found to be more than double the electron temperature as observed in experiments. And we find that the density blobs are scale approximately close to ASDEX measurements. And more realistic features, for example, shear and neutrals and improved collisional modules, they'll be incorporated in our electromagnetic gyrokinetic model for better comparison with the experiments. This is the technology.
Good, thank you very much. We are all virtually clapping. Questions from anybody? Go ahead and raise your hand or go ahead and speak. We are running short on time, but if anybody, are there any experimentalists here? Probably not, but I'm just wondering. Well, I'll ask one. Just so if you go back to the comparison with the paper, you had a number of different plots versus collisionality. Go back yes, this slide. Yeah, so you're maybe you could comment some more, but you're hinting that maybe we're just getting up to the transition in collisionality.
Right.
The experiment sees a much sharper transition, and we haven't quite gotten up to those.
This data point is pretty different. Even though in experiment they had somewhere here, in simulation we are here. But yeah, otherwise we are probably able to capture this transition. Yes.
Yeah. Okay.
However, more runs need to be Yeah. Given anything.
Okay. Any other questions?